Okay, let's jump right into this stack of source material you sent over. We're doing a deep dive today into some, well, foundational geometry stuff, measuring the edges and the space inside flat shapes.
Right, perimeter and area, that's the core of it. Perimeter, the sources say, is just the length of the boundary, like walking around a field.
Yeah, the fence line. And area is the space inside, so the grass in the field or how much paint you need for a wall, that kind of thing.
Exactly. And a key thing the material points out is the units. Big difference. Perimeter is a length, right? So just centimeters, meters, whatever. Linear.
Okay.
But area, that surface. So it's square units, cm squared, meter squared.
Right, MLA. And they highlighted that common mix-up about x square meter versus x meter squared.
Yes, good point. X square meters is just the total area, like 5 square meters. But a 5-meter square describes the shape, a square, with sides that are each 5 meters long.
Ah, I see. So its area would be 25 square meters. Big difference from just 5 square meters.
Precisely. Wording matters there.
Okay, so our mission here is to dig into these formulas, these examples in your sources, and kind of pull out the useful bits for you listening. Let's start with triangles.
Sure. The go-to area formula is the classic. 1/2 times base times height.
1/2 base height. Got it.
And remember, any side can be the base. You just need the height that's perpendicular to that specific side.
But what if you, only know the lengths of the 3 sides? No height given.
Yeah, that happens. That's where Heron's formula comes in. Super handy. The sources show it well. You find S, the semi-perimeter, just add the sides, A, B, C, and divide by 2.
Okay, half the total perimeter.
Exactly. Then the area is the square root of, well, it's S times SA times SB.
Right. I saw that example. They use sides 17, 8, and 15 centimeter. Heron's gives you 60 centimeters squared for the area.
60 square centimeters.
What I thought was cool was how they then took that area 60 and used the basic area formula, area 12 base height, to figure out the height relative to the longest side, the 17 centimeter one.
Yeah, working backwards almost. Shows how the formulas connect. They found the height was about 7.06 centimeters.
Exactly. It's not just isolated equations. Okay, moving on. Quadrilaterals. 4 sides.
Yep. The sources mention one way to find the area is using a diagonal. You draw one diagonal, then drop perpendicular lines to it from the other 2 corners.
Okay, like little heights to the diagonal.
Sort of, yeah. The area is half the diagonal's length times the sum of those 2 perpendicular lengths.
Interesting. And what if the diagonals cross at right angles, like a rhombus?
Oh, then it's simpler. Just half the product of the diagonals. Diag 1 times diag 2 divided by 2.
Nice. And of course, the basics, rectangles and squares. Can't forget those.
Definitely not. Rectangle area is just length times breadth. Square area is side times side squared. The sources use these a lot for practical things, like calculating the area of a pathway around a rectangle. You find the big area, find the small inner area, and subtract.
Makes sense. Layering the basics.
Right.
Circles them.
Circles. All about that magic number pi. Pi is the ratio, always constant, between the circumference and the diameter.
So circumference is pi times diameter, or 2 pi times the radius, since diameter is twice the radius.
Exactly. C key equals 2 par, and the area, that's A equals RR. Pi times the radius squared.
The examples with wheels were really good, I thought. Made it concrete. Like if you have a wheel, radius 28 centimeter, you find its circumference. That's how far it rolls in one go.
Right. And then you can figure out, okay, to cover 4.4 kilometers, how many times does that wheel turn?
Yeah, the source calculated it out to 2,500 rotations for that specific example.
Or you can flip it. If you know how fast the wheel is spinning, say, revolutions per minute.
You can calculate the vehicle's speed, like that other example. 28 centimeter radius wheel, 300 RPM.
Yeah, that works out to over 31 kilometers per hour. It directly links the geometry to the actual movement.
So bottom line, these aren't just abstract math formulas you memorize for a test. People are using these constantly, calculating paint, carpet, field sizes.
Absolutely. Or figuring out mechanical things, like how sorry your car goes based on tire size. It's the language for quantifying space.
Okay, one last thing that really stood out from a few examples, like number 17, 26, 33 in the sources. It's this idea, take a fixed length of wire, same length.
Right.
You can bend it into a square, or maybe an equilateral triangle, or a rectangle.
Or even a circle.
And even though the perimeter, the wire length is identical in every case, the area inside can be really different.
Hugely different sometimes. Those examples show it clearly. A square usually holds more area than a skinny rectangle with the same perimeter.
And the circle holds the most area for a given perimeter, right?
And among common shapes, yes. The circle is the most efficient shape for enclosing space.
Which kind of leaves you thinking, doesn't it? About how much the actual shape matters when you're trying to optimize space or use material efficiently. something to mull over.